So, hi everyone. First of all, thanks for coming. That I hope you can see that I'm changing the slides so you can see that. Um, this is fourth year of the NIDIT. NIDIT is the Novel Input Devices and Interaction Techniques workshop, which is in the IEEE VR. Last year, we had more than 90 attendees. That was like really big achievement for the all organizers. And in this workshop, we aim to provide, a kind of a forum like where people come together and discuss new input devices, interaction techniques that are used in virtual reality and augmented reality. Our workshop is mostly focused on the applications, and that when the first NIDIT started, we encourage people to have demos, or real life demos. So you were able to go there and try actually what the researchers did, and you can get like an idea what is happening. But unfortunately, because of COVID, we cannot do this year. Myself, Anil Batmaz, I'm the lead organizer of this workshop this year. With together, Francisco Ortega, Rob Taylor, Adalberto Simon, Wolfgang Schützlinger, and Benjamin Weyers, we organized this year's NIDIT. So this year, as in the previous year, we're gonna have really good workshop papers. This year we had 3 submissions, and that, as I said previously, for NIDIT, we asked people to have a short demos. But since that's a virtual workshop, as last year, you cannot gonna try the new input devices and interaction techniques. That in the selection process that we asked, there were like reviewers who reviewed the paper. So each paper was double-blind reviewed. So we had, this is how we have our submissions. So we will start with the 3 presentations, that each presentation is going to take 10 to 12 minutes, and we're going to have 3 to 5 Q&A session. And then we're going to have a 1 keynote speech. The Anil Steed from UCL is going to give the keynote speech this year. Then we are going to have a panel discussion with the Amy Bennett, Wolfgang Schützlinger, and Anil Steed. Previously, Amy and Wolfgang were our keynote speakers, and we asked them to again come to NIDIT and discuss since their the keynote speech, what changed in their environment, in their research environment, and this is what we're going to discuss. We're going to have a few breaks between the paper session and the keynote and panel. And that we are going to follow the IEEE VR schedule, and we are not going to have any demos this year because because of the online format, we cannot provide this. For the questions, you can use Zoom and Discord. I will look at the Zoom, I will look at the message in the Zoom. I encourage people to ask questions to our both with the paper presenters and in the panel. And if you want to use the Discord, you can use you have to go on the left-hand side. You're gonna see a slide bar, and you will just go down. You have to find the NIDIT workshop. The name is written NIDIT Workshop on Novel Input Devices and Interaction Techniques, and you will just go there. You will find the workshop there, and you can write your questions. I will again try to look there, but I also encourage people to use Zoom so that it will be more interactive. If you look at the Verbola, there's also the Verbola where you can use, but the Verbola is not available for the workshop. So it is possible for you to interact with the speakers and with the other attendees, but we will not able to get your questions from Verbola. So we can start that. We are going to start with the first paper with Impress Input Multi-Touch Progressive Refinement Selection Strategy. And I am just going to give the permission for the Rob Tether to play the video. I think, Rob, is it possible that can you play it or?
Can you see that? I just shared my screen.
Wait. Yes.
Okay, great. Okay, so thanks, Ufuk. Great introduction. My student Elahe, who has now graduated, did this work and it couldn't make it to the workshop today, so I asked her to record a video of this instead, and I will stick around to field some questions if you have any afterwards. And of course, as Ufuk said, feel free to shoot these over to the Discord after, and Elahe will be in later in the week. So I'm going to play the video now and hide myself.
But I think we cannot hear the sound.
Oops. Yeah, there should be sound. Let me try this again. Sorry about that, everybody. There, share sound. That should do it. Let's try that again.
Hello everyone, my name is Elahe Samimi and I graduated with a Master of IT from Carleton University. This presentation is about improved multi-touch progressive refinement selection strategy, which we call it IMPRESS, and I worked on this project with my supervisor, Dr. Robert Tedder. IMPRESS technique is a combination of two selection methods, progressive refinement and count marks. Progressive refinement is a relatively recent class of selection techniques introduced by Cooper, and count marks is a menu-based selection technique that uses a smartphone as a controller. We designed a multi-touch progressive refinement technique to improve selection speed while offering precise accuracy. Like other progressive refinement techniques, the technique involves several steps to accomplish selection. The first step is selecting target area. Like squad technique, users do not need to be precise in the first step. Instead, they can select the general target area. Like other progressive refinement techniques, this employs raycasting with a selection sphere at the ray intersection point. Objects in the sphere are selection candidates that proceed to the second step. The second step is about displaying candidate objects. The initial selection typically yields multiple candidate objects, which we distribute on a quad menu, like squad exactly. We start by arranging objects from the outside of each triangle and continue to the middle, and it's obvious that denser virtual environments generally have more objects in the initial selection. To balance objects equally in quads, we dedicated one object at a time to each menu, first filling all the first positions of each quadrant, then each second position, then each third position, and so on as shown in the image here. And finally, we display the quads. If there are 4 or fewer items in each quad, we also present the position number of each object on each quad, which corresponds to how many fingers would select the object with a directional swipe. Step 3 is the main difference of our technique with previous ones. Step 3 is about selecting one object in the quad menu. The user next refines the selection to remove undesired objects. We break this step into two sub-steps. First one is indicating target via multi-touch. This step actually employs the idea of count marks. If there are 4 or fewer objects in each menu, the user can select the target outright by touching the screen with the number of fingers corresponding to the target's position. Upon touching the screen, all candidate objects corresponding to the finger count are highlighted to yellow. For instance, in this figure, the user put one finger on the screen to select a blue book in the first position. The next step is to select target area, the target by swipe. After step 3.1, users finalize their selection by swiping their fingers in the desired direction. Upon moving their fingers in the desired direction, the selected quadrant highlights green. Again, in this figure, the user is swiping left, highlighting the left quadrant. Selection occurs when the user swipes their finger to the edge of the touchscreen. The technique currently supports only 4 primary swiping directions, and this could be extended to more, for example, 8 directions to display more selected items or to distribute items further across each menu. If there are more than 4 candidate objects in each quad, like the left image, users must first refine the candidates further before multi-touch selection is possible. Users can swipe their number of fingers on the touch screen in the desired quad direction to first drill down and refine the candidate sets. The items for the selected quad then distribute, and the process repeats from step 2 until 4 or fewer items appear on the quad. Okay, for the experiment section, actually, we recruited 12 participants. We used an Oculus Rift CV1, a Samsung Galaxy S8, and a PC with an Intel Core i7 CPU. To comply with COVID-19 measures, we dropped off key hardware at participants' residences following social distancing protocols. Participants use their own mouse and keyboard accordingly. For the software, we developed 2 applications, one running on the PC and the other one on the Samsung Galaxy, the smartphone, and both were designed in Unity 3D. We employed a 3x3 within subject design with the following independent variables and levels: selection technique and density, which both of them had 3 levels. We also had 3 dependent variables: search time, selection time, and error rate. For all the analysis, we used two-way ANOVA with Bonferroni Dune postdoc. And for the search time, actually, search time is the time that users spend to find the target object in the virtual environment. There was a significant main effect of density and search time. However, there was not any main effect of the selection technique. It means that finding a target would clearly take longer in a denser environment, but the selection technique, which primarily differs after the initial selection step, was not expected to influence search time. Selection time is how long participants spend navigating the quad menu after initial selection of candidate objects. The main effect for both selection technique and density were significant, as was the interaction effect between selection technique and density. It means that Impress offered faster selection time than the other two techniques and was generally less affected by density than the other techniques. An error occurs when selecting the wrong quad during menu navigation. There was a significant main effect of the selection technique on error rate. Neither the main effect of density nor the selection technique density interaction effects were significant, and we were surprised actually that squad's error rate was much higher than the two other techniques. Finger error rate. Naturally, participants sometimes use the wrong number of fingers within press. We recorded this error, this finger error rate, separate from navigation errors, but since it only exists for impress, we do not compare it to the other techniques. Instead, we used one-way ANOVA to compare across density. The main effect for density on finger error rate was not significant, and finger error rate was generally low. We developed Impress, a VR selection technique that combines progressive refinement with the count marks multi-touch marking menu technique. Impress offers better selection time and accuracy than other techniques, especially in dense environments. And our results added to the growing literature on smartphones as VR controllers. One of the main limitations in this project was performing the experiment remotely because of COVID-19. Conducting the experiment remotely potentially introduced more variability in our results. On one hand, this enhances our study's external validity, but also highlights the difficulty in conducting remote experiments. Participants had to set the equipment themselves, which required setup time and consequently limiting the number of trials and densities to keep the experiment duration reasonable. And for this reason, we also excluded any tutorial or practice session. Since density order was not counterbalanced, this likely means that there was a sharp learning curve in early trials, primarily affected the low density conditions. Now I would like actually to show you a quick demo of the technique. Thank you so much for listening.
Okay, thanks everybody. So that's Ellie's presentation. So I'm happy to field any questions. I think we have a few minutes for questions. Is that right, Ufuk?
Yes, yeah, we have 3 minutes for the questions. Are there any questions? First of all, I cannot see any questions in the Discord. Tort wants to ask a question. Yes, sir.
Sure. And I'll preface this by saying I didn't do this work myself, so I'll do my best in answering these, but it might, if I can't answer it, I'll refer you to put a message in Discord for Ellie to get. So Tord, go ahead, please.
Yeah, I was just wondering, in the experiments you had, like I saw that there was, for example, they had to pick the blue book, for example, between the others. How do you think this would, or have you tried this with a more, let's say, a more natural way, where you have different types of books and they have to like browse through them and figure out what they want?
Yeah, that we haven't tried that yet. That would make sense. I think actually when we started first talking about this, I suggested the if you've seen the old 3DUI contest virtual grocery store that was used in a lot of the original squad work, for example, I suggested using something like that, but I don't remember why we didn't end up using that. But definitely you know, more naturalistic sort of scenario would make sense to test this in. This was kind of, I think we went with books just because it was something that was easy to model, easy to put a lot in, and it allowed us to create different densities by you know, scaling the books to make them thinner, stacking them, and this kind of thing. So I think that was the rationale for why it was a, you know, virtual library sort of setup.
Yeah, thank you. It's a very interesting technique, I must say.
Thank you.
Any other questions? Is also not on Discord, so I can ask a question.
Sure.
So you mentioned that that in the experiment you use 4 cuts. Why not 5 or 3? I mean, what was the reason? That's the first question. And second of all, what if you need to go, like, for example, 16 or 20, what would happen?
16 or 20 quads.
Mhm.
Okay, well, this is in part based on marking menus, right? And that was so let me take a step back here. The count marks technique that we've previously published was what was kind of the key difference between this and the sort of conventional squad technique, right? And we had devised that previously for use in sort of like imagine in augmented reality scenarios where you might be using a Google Glass or a Microsoft HoloLens or something like that, and you had a smartphone handy that you could just do these little basically marking menu type gestures, but with multi-touch to kind of shortcut through parts of the menu. And so this is where we basically mashed this up with progressive refinement, or specifically the squad technique. So I think you'd find this is why we went with 4 quads initially, was partly just to kind of align it to what Hedges Copper had done with squad, but also partly because this is sort of a limitation with marking menus, right? That you 4 directions is easy, 8 directions is about still doable. Beyond that, it gets hard to pick the specific directions, and in particular, you can imagine, like in this case, we're talking about on a smartphone screen, but also with up to 4 fingers at once. So something I want to do is go back and try this with 6 directions or 8 directions and see how far we can push it where it still works. I think with for the case where you have up to 4 fingers on the screen at a time, there's benefit to having 8 directions, because you can basically short circuit more of that hierarchy faster that way, right? But it's I think, I don't know, we haven't really tested that yet, but it's something I want to go back to. It's the short answer, I guess.
Great. Thanks. Any other questions for Rob? No. Okay, perfect. Thank you very much, Rob. Thanks a lot.
Thanks.
So now we are going to go with our second author and second paper, my eyes hurt, effect of jitter in 3D gaze tracking. So Moaz is going to present this paper. Moaz, are you here?
Yes, I am here.
Okay, perfect. You can share the screen.
Thank you. So can you see my presentation right now?
Yes, we can.
So hi everyone, I hope everyone is doing okay. I'm Moaz. I am a second year undergraduate student at Calderhouse University. I'm studying mechatronics engineering, and today I want to present to you the paper My Eyes Hurt, Effects of Jitter in 3D Gaze Tracking, that was authored by me, Mr. Onay, Professor Wolfgang, and Professor Anil Ufuk. So to start off, in the physical world, we're always touching, carrying things, pinching, pulling, pushing. This is how we interact with our physical world. On the other hand, in virtual reality, there are many ways to manipulate the virtual environment, and one of the most important ones is selection. Seems pretty basic, but selection has mainly 2 parts: pointing, where you are aiming at what you want to manipulate, and then selecting, where you are confirming. And you can see in one of our participants here, she is pointing using her eye, and then she will be selecting using her hand. This is our experiment, actually. So moving on, jitter. So when we're dealing with VR, we're dealing with jitter a lot. And jitter is fluctuations in signals, and it basically represents itself as something that is happening to this picture right now, shaking around all over the place. And it can be caused to many reasons, including inaccuracies in the tracking systems, filtering algorithms can also produce jitter as a side effect. It can be the interference of some signals. It can be our mistake by hand tremor or unintentional movements and many other reasons. And in VR, jitter is more prominent because it's flying in thin air. We are carrying it. We might get tired, so, and doesn't have any physical support. Unlike the mouse that you are using maybe right now, it's stable on a table, but in VR, it's flying all over the place. It's hard to keep stable. Now, next on, we can go to gaze tracking, and as simple to put it is, gaze tracking is the technology that tracks where your eyes are going. So you can imagine just two laser beams going out of your eye and just aiming wherever you're looking all around the place. Now, I do think that most of you are now trying to figure out what is in the reflection of the VR on the surgeon's head. So you can just imagine two lasers just aimed there. Now, gaze tracking has been proposed as a selection method, and one of the reasons is that because it's very fast and it can be up to 900 degrees per second because the eyes are all over the place all the time. Another reason is for hands-free usage. So when you have a task like the surgeon, for example, he is busy working on the patient. If they want to select something, he can actually select using his eyes and confirming with a voice command or a blink and so on. Now, again, in gaze tracking, we experience jitter, and it can be caused by blinking or by our eyes moving outside the sensor. By the technologies, the algorithms can produce it as a side effect and so on. Now, previously, there has been studies that tried to see the effects of jitter and on the user performance in VR controllers. And the studies came out to find that between 0 and 0.5 degrees of rotational additional jitter, it didn't really affect the execution time of the experiment. However, with anything that is more than 1 degrees of additional jitter, the error rate increased significantly and the throughput decreased. And you can see one of the graphs on the right, on the first one on the right, is for that study. Now, another follow-up study eliminated the Heisenberg effect. Now, the Heisenberg effect is when you're carrying a controller and you're trying to select, you can press on it and this press kind of shakes the controller around. And what they did to eliminate this is to use a bimanual selection technique where one of the hands, the dominant hand, will be aiming and the other one will be on a space button, maybe trying to confirm the selection. They also did a white Gaussian noise analysis, and they also, and in the end, they came up with very similar results, with 0 and 0.5 being not so affecting, but anything more than 1 had a great significant effect. Now, studying jitter in gaze tracking is important because if you are introducing it as an input method, that means you have to know where is the benchmark for what is acceptable jitter, where it's too much for the user and it lowers the experience too much and makes it hard to use. Previous studies have looked at gaze tracking and jitter in gaze tracking. However, in this study, we were working with rotational jitter, and we created the study with angular measures. Everything was in angular measures. And we also wanted to look at the depth perception of the targets, or the target depth, as we dub it. And in order to explain it really fast, if you see in the first picture here, the two spheres look very similar in size. I also put these lines in order to just show that they are on the same level. However, if you see them from far away, they are actually at different scales. And we wanted to investigate that. How will depth affect, like it looks the same for the user, but it actually is further, and will that affect or not? Now, we hypothesized that with increasing levels of jitter, the performance and experience will be decreasing. And also the second hypothesis is that the depth will affect the performance and experience. For our user study, we had 12 participants, 5 female, 7 male. The ages were ranging between 18 and 28. We used a PC with an i7, 32 gigabytes of RAM, an RTX 3070, and an HTC Vive Pro I with Tobii eye tracking. Now, for experiment design, we were using an ISO task. You can see it in the picture. It's put in a circular manner with 11 targets. So basically the experimentee would come, they would fill up a demographic first, and then they would do the experiment where they are trying to select with their eyes and confirming with the space button. And I also put something to just explain the colors here. So the small yellow sphere here is the cursor that is following the gaze. And this is what's going to be shaking when we are adding our jitter. The gray is the unselected, the orange is the next target, the blue is what is selected by the cursor at the time, green is a hit, or what is when a participant correctly selects a target, and red is a miss, when they actually miss the target due to jitter or anything. Now, our independent variables, we had 4 levels of jitter, 0, 0.5, 1, and 1.5 degrees. Of course, it's all added in. We had 2 depth distances, 1 and 2 meters. Now, again, even if it's further, it will look the same because we are scaling everything up. We had 3 target distances, 6, 9, and 12, and we had 3 target sizes, 2, 2.5, and 3. So when you multiply all this, you can find out that 792 trials were done per participant. We were testing for our dependent variables were execution time, error rate, throughput, and accuracy. Now, for our results, you can notice that with the greater depth, the execution time increased, and the error rate also increased. So we can see that depth did have an effect actually on the performance and on the error rate. In the graph on the left, you can see that with increasing levels of jitter, you can notice that there is significantly more errors being created, but also with the depth, that the depth consistently had more errors. So the higher the depth, the more the errors were happening. So even with no jitter, the depth had an effect. You can also notice that at 1.5 added jitter, the difference between 1 meter depth and 2 meter depths weren't so high. So that means that the jitter was high enough that the depth didn't really matter anymore. And in the last graph, we can see that. Okay. I think I did something. Can you see my screen?
Yes, we can. But it's on full screen.
Okay. Yeah, perfect. What? Okay, wait, I will reshare real quick. Okay, am I back on the same slide?
Yes, yeah, perfect, you can go on.
Okay, so we can see also that the accuracy had decreased with increasing depth. Now, for our discussion, we were using the Cooper's angular fits law to model our data. And actually, the reason we named the paper My Eyes Hurt is because all the participants did say that they had some fatigue in the demographic that they filled after the experiment. But one of them wrote that their eyes hurt, and they all were telling me as I ran the experiment that it was so confusing. Now, we also noticed that there was a versions accommodation conflict that was affecting the experiment, and that actually another thing that must be mentioned, that the HTC Vive Pro I also has 0.5 to 1.5 degrees of jitter. So what we were adding is even more than that. And previously, other studies that experimented on jitter and gaze tracking, they were going up to 2 degrees of jitter. But as we set up the experiment, we were trying it around 2 degrees of jitter was too high and it made everything too hard. So we realized that it would be better to stop just at 1.5. Now, to conclude everything, we evaluated the VR gaze tracking devices based on angular measures. So that's why the targets and everything was measured in angles. The error rate significantly increased with 0.5 jitter. The gaze tracking was affected significantly by the depth, which is very important. And for future research, we want to include the effect of stereo display deficiencies. And we know that versions accommodation conflict has a significant effect on the throughput of stereo displays. However, we want to conduct a study that will focus on multifocal displays in the future. And that is all from me. Thank you for listening. And if you have any questions.
Perfect. Thank you very much, Moz. So let me check. So in the chat, there are no questions. In the court, there are no questions. Furkan has a question. Yes, Furkan.
Hello, everyone. Firstly, thank you, Moz, for this great presentation. I want to ask about the experiments. Like, did you collect any user experience data during the experiment? Like, how much the participants get tired during the experiment? I really wonder to know that.
Well, before the experiment, the participants filled a demographic questionnaire, and then after they were done, they also continued the questionnaire. And in there, we did ask if they had any physical or mental fatigue. And we also asked, did you like the jitter? Did you not like it? Did it make it hard? They also commented, and this is where we got the title for the paper.
Okay, thank you.
Any other questions? Chat, there's no one. In the court, there's no questions. Yeah, okay, perfect. Thanks, Moz, that we are perfect. Sorry.
Oh, I have one.
Yeah, Maya, yeah, come.
Yeah. So because I saw that the qualitative, but did you take any kind of plot or something to see if the effect of discomfort increases with more jitter or less jitter, or was just the general comments of the general experiment?
Sorry, could you repeat the question?
Oh, because one of the results was that the jitter make them fatigue their eyes. But was there any kind of results that show if the increasing jitter make them more discomfort, or was just the general experiment that make them feel fatigue?
Well, with more jitter, they generally had more errors and more execution time. So yeah, but we didn't model for the fatigue. We modeled for the jitter. They just told us about the fatigue, and they also in the questionnaire they were saying the level of fatigue they had.
All right, thanks.
Okay, perfect. Thank you very much, Moz. And we have the last presenter, the last paper, study of thin polymer precharge multipoint tactile device. And our presenter will be Junji Son. Is Junji here?
Yeah, thank you.
Okay, perfect. Thank you very much.
Can you see my slide?
Yeah,
Okay.
everything is great. Yes.
Yeah. I present following title. It's a tactile device research, and this research is executed mainly. I'm a visiting scholar of the UC Berkeley with Professor Liu Ling. Background is yesterday. We have a great talk of the Batmaz by Professor Huey. These tactile devices use interactivity is specified, and it is important. And many XR technology and 5G technology open the new communication of the haptic and tactile sensation. One example is MIT Media Lab making a bidirectional force shape display. It's fantastic. I review a tactile device, a pin device, and galvanic and MEMS actuator. And basic is an opticon. Opticon is a very braille display. Dimension is a 100 micron, and it's a slow but very good ability for the blind. And next is a crank type. Crank type is a very big mechanism. And another is a vibration. Smartphone has a vibrator. This vibrator is only one stimulation. And another is a ionic conductive polymer. It's a little weight. And another is a hydraulic displacement amplification mechanism and magnetic and shape memory array. There are many research. And another is a ultrasonic and air jet and galvanic stimulation. One research is Kajimoto group make a finger. It combined is galvanic and skin deformation is combined. It's a high level haptic and tactile feedback. And another is mid-air ultrasonic. It's a little big actuator. And surface haptics. We have a review paper and many vibration and friction and net tangent force. And one is electrostatics. It is a high voltage. It requires high voltage. And another is this is also electrostatic. That it can represent a surface roughness sensation. Our study is basic research is executed by a Professor Zong. He was a researcher of the UC Berkeley, and now he is a professor of Macau University. He developed a piezoelectric device using a polymer-based. Piezoelectric means it can be an actuator and sensor. And sensor is a complex device. Voltage is generated, and the actuator is if we apply the sinusoid signal, device is vibrate. And it is very surprisingly, I usually build a MEMS device by a PZT. PZT is a ceramics device. PZT is only 200 and 400 picocoulomb or picometer per volt is a piezoelectric constant. But this device is 4,000, almost 10 times higher than PZT. PZT is a very familiar device, for the printer or many actuator using PZT. In this study, we will extend the multi-point tactile actuator. And another challenge is this device is required pre-charge. Then we'll investigate extend the pre-charge ability. Process is first will be the flat plate, and we're using a speed coat and silicone rubber is spin coated, and almost 0.2 millimeter thickness film is made and solidified, and punching the hole, and we need to adhere the film and silicone rubber. Then first we need to add the hydroxyl group to add the silicone rubber by oxygen plasma, and sintering aptes. And another is a FEP film, is a I'm sorry. FEP film is we use 50 micrometer and 25 micrometer, and electrode is evaporated 200 nanometer, and I will add the hydroxyl group and adhere silicone rubber and 2 FA film, and also charging almost 1 kilovolt, about 20 minutes, and we measure the vibration. Vibration is measured by a film type pressure sensor, and we use weight to contact to pressure sensor. And the result, we confirm the sensor function. If we weight 50-gram weight slowly on this device and measure the voltage, then we can measure almost 35 volt electric generation is confirmed. And next, I will explain actuator function. We have 2 types of patterning. This actuator needs a hole. One is almost hole ratio is 10% L1 type. L2 type is hole ratio is 28%. Then we charge 1 kilovolt 20 minutes. Then we measure charge voltage by electrostatic sensor. This device is almost 700 volt is observed. And 3 weeks later, charge voltage is not so much different. And previous mentioned, we need to extend the charging period. Then potassium doping on the SiO2 glass is a very long time charge holding. Then first we using a 0.05 millimeter SiO2 glass plate, and this plate is potassium doping by 450 degree, 20 minutes, and charge only in this time only charging a glass 200 more than 300 degrees C, 20 minutes. Then L sign is only inserted between silicon rubber and FAP film. And L4 is we are using almost 0.03 to 0.04 SiO2 glass beads is almost 0.5 weight percent mixed in silicon rubber. This glass beads is potassium doped at 600 degrees C over 20 minutes. In this case, L1 is a very good ability, and 3 weeks later is also this ability. This figure shows frequency. Virtual reality, we need to almost 50 hertz to 300 hertz is required. Then we measure vibrate force at this frequency, and L1 is a very good ability, and L4 is also good ability. The potassium glass beads blending. And multi-point device, we patterned the electrode, and other side is a flat electrode. We have almost 8 pattern. It's a building here. And vibration force, and orange is a charge bolt. Charge bolt is less than a large size device, but we have this charge bolt, and vibration is almost in this large device is almost 0.08 Newton. In this case, 0.06 Newton in this case. And frequency is almost flat, and charge time and 3 weeks later. 3 weeks later, vibration force is a little improvement. And we also tried direction task. We build a 5x5 array and direction, actuate direction recognition. We build this device, but we use conductive polymer adhesion. Then we expect only one person, and contact adhesion is spread. Then device cannot work again. Then we need to improve. Yeah, the conclusion. We confirm the piezoelectric feature, and silica beads and potassium dope is effective for long time charge, I think. And 70 to 300 and almost 20 volt is not primary, plus minus. Effective voltage is 20 volt is a reasonable offsetting. And the multi-point device is we develop and confirm the vibration, and we need to improve the wiring method. Thank you. Thank you for listening.
Thank you very much. Let me see that if there are any questions. There are no questions in the Discord, and I'm checking. And it seems there are also no questions in the chat. So I have a question regarding this novel device. Are you planning any user studies?
Yes, yeah. I have some contact with Professor Kawashima at the University of Tokyo. He is developing a surgical robot. Yeah. If we will complete the device, first I will supply to Professor Kawashima for the surgical robotics. Yes.
And then how about the virtual environment? Are you planning any kind of experiment with the virtual reality or augmented reality?
Yeah. Yeah, I also try to metaverse. But yeah, perhaps I'm searching a co-researcher, perhaps Professor Saga at Kumamoto University. He has a very curious about our device there. I want to co-research with Professor Saga at Kumamoto University.
Perfect. Okay, thank you very much.
Yeah, thank you.
Are there any? I cannot see any further questions. So thank you very much.
Thank you.
Actually, now that we let me share my screen. Again, so that we finish our presentations, and we actually supposed to have a short break, but I think that we already filled the break. So in terms of catching up with our schedule, I will just continue with our keynote speaker, Anthony Steed. I mean, if is Anthony here? Yeah, Anthony is here. Hi, Anthony. So I'm just going to present Anthony for like really fast. So today, Anthony is going to talk about what we can learn from consumer VR games. This is his research, his speech title for today. Anthony Steed is the head of virtual environments and the computer graphics group in the Department of Computer Science at University College London. He has over 25 years experience in developing effective immersive experiences. While his earlier work focused on engineering of displays and software, more recently it has focused on engagement in collaborative and telepresence scenarios. He received IEEE TVGC 2016 Virtual Reality Technical Achievement Award. Recently, he was a visiting researcher at Microsoft Research, Redmond, and an Erskine Fellow at the Human Interface Technology Laboratory in Christchurch, New Zealand. So, Anthony, I'm just going to stop sharing my video. Sorry, this one. And yeah, you can share it. Thank you.
Okay, great. Thanks for that nice introduction. And I should note that, as Anil said at the end, I was an Erskine Fellow at Christchurch, which means I was in New Zealand, where we're all supposed to be. And I had a delightful time in Rob Lindeman's lab. So I am very disappointed to come back and see the lab and get a hamburger at Burger Bros. So I'm going to talk about what we can learn from consumer virtual reality games. And this is going to be, this is sort of an extended version and some more thoughts on our paper that we presented at ISMAR last year, which is a result of a novel process for sort of trying to write a paper, which again is rather fittingly happened while I was on sabbatical in Christchurch. And being on sabbatical, I had a bit more time to play some consumer VR games, but no time to sort of build and run a long experiment. So we came up with this process for sort of trying to find good examples of things that we could learn from all the good design that was out there, and try and get some input, not just from the consumer VR game community, from the academic community, but the actual developers of these consumer VR games. And a final piece of introduction, there of course, the game development community is massive, and obviously it has its conferences, and partly this was a little bit of guilt from a talk that a panel that we held at the Game Developer Conference, I think in 2016, where we tried to kickstart a sort of collaboration between the sort of game developer community and the academic community. And the question at the end of the session was directed to myself and others, including Doug Bowman, was, we're developing games right now. What can you, academic community, tell us about the games that we're developing? What techniques could we use? And to be honest, we had to sit and think for a while, and started talking about the types of research we do, and so what we, the sort of classic sort of split of consumer interaction techniques and the devices. And it'd be very clear that actually there wasn't a lot of solution to the problems that they had. And I'll come on to why, but this has been at the back of my mind for a few years, in that there's a lot of academic research and there's a lot of consumer virtual reality development, but there's not it'd be nice to find ways to communicate and share results and share information. So the first premise is that millions of hours have now been spent in thousands of consumer virtual reality applications. So this is a view from Steam last week. I can't remember exactly what day. You have a look yourself. You probably see slightly different numbers. This is based on the fact these are, I'm based in the United Kingdom, so the numbers for you might be different. But there's somewhere between 6,337 and 7,950 VR applications on Steam VR. The reason there's two numbers is because all I've done is typed VR into the search box and got 7,900 and whatever. But actually Steam has a category of games which are called VR games, and there it says there are fewer. So the narrow by tag says 6,000. So it doesn't. I don't know if that's VR games that I've forgotten. VR games that I've forgotten to put the tag, or games that just don't have anything to do with VR. But anyway, the key thing is there's lots of applications, and millions of hours have been played in these. Right, so 6,000 games. That's only 300 hours per game, and there are millions of devices out there. So we're only expecting each device to be used for an hour, and we're already at a formidable number of hours playing these games, the likes of which we'll never see in the lab. The other thing to note is that many thousands, tens of thousands, probably hundreds of thousands of hours have been put into developing these games. And again, more effort has been put in developing consumer VR games interaction. There's probably been spent on VR research in labs, and that's happened over quite a short period of time. And there's lots of novel interaction techniques. So there's lots and lots of things that you see in games which are, I find surprising and delightful, or cause me to say, well, you shouldn't have done it like that. There's a better technique for that. So So that's just my personal reaction to a few of these games, and you know, I've got some favorites, some VR games that I've played a lot, and you know, there's techniques that I like. So the question is really, what can we learn from all of that? And there's the reason that we didn't have a lot to talk about at GDC is because actually 3D user interface research is tackling a sort of different set of problems than the consumer VR developers. And here's a few framing issues that I think are really interesting, because these are things that consumer VR systems deal with, that academics don't or have a different opinion about. The first is that if you look at all of these consumer VR applications, you're already in a very narrow funnel of user interface. So while there have been lots of different consumer VR systems, there is really only one short axis, which is it's a head-mounted display, and it may be 3 DOF track, 6 DOF track, and then if you've got a 6 DOF track, has it got hand controllers that come with it? And that's quite a short axis, and to some extent, the tail end of that, the 3 DOF devices, the 6 DOF devices without hand controllers, are essentially being ignored, mostly ignored now. And you can challenge me on that, and we'll have a discussion afterwards, because it is still a way, in education, that's still a target device. But for many of the applications that are on consumer VR, that are being sold on Steam VR, you've got to have hand controllers now. And if you don't have a head position, you're going to struggle a little bit. Now we can discuss that. It's quite difficult to narrow down come up with a complete specification of this system, because there are unsurprisingly there are annoying differences between, say, a Quest and HTC Pro I, but pretty much the same. So no caves. Right, no touch tables, nothing that we would well be within the scope of IEEE VR or this workshop. And I've written papers, or my students have written papers with me about the differences between trying to implement certain interaction techniques if you use a projection system versus a head-mounted display, and what the subtle differences between the two are. But the sort of projection displays in the home are that's definitely, people keep sort of mentioning it, and there have been a couple of sort of attempts, at least from the research side, to sort of promote this as the future. Every so often, a rather excited magazine writer comes across their first cave and starts saying it's the future, which those of us who've been around for a while start chuckle, because we spent a lot of time on caves because they were much better than head-mounted displays in the 2000s. So that's the first difference. Very few novel devices. There's a lot of interesting work, a lot of it from one of the groups that I spent my sabbatical at. Thanks again for Anil for mentioning it. I spent 6 months in the Microsoft research in the group that's led by Ken Hinckley, but includes Ayal Ufuk and Mike Sinclair and Mark Gonzalez Franco, where they build a lot of handheld controllers, for example, and they've got a series of these controllers that do really interesting things, and that's great 3D user interface research, haptics research, and so on. But it's not entering the consumer domain in the next couple of years. Who knows, for a 5 to 10 year horizon. Okay, so that's the first framing issue. It's a fairly narrow set of inputs, and to some extent, I think we have to consider that the Quest 2 is going to be around for a while. Right, so this may become a lowest common denominator. There are millions of them. They're not going away anytime soon. It's cheap. It's very accessible. And if you're going to target these millions of users, then that's the base platform that I think will be sticking with for a number of years. The second framing is it needs to deal with the real world as users encounter it. So one of the particular issues that consumer VR deals with, and we'll see, we discuss in that paper at ISMAR, is that you don't get to clear the space for the particular application. So again, when we do a lot of work in the lab, anybody that does redirected walking, including my lab, I have a student, Ben, who's been working on redirected walking. You need a certain sized lab. Otherwise, your experiments aren't viable because there's a minimum space it currently operates in, and I'm looking forward to reading some papers about that at the conference coming up. But of course, in the consumer domain, you've got to deal with the space as you find it. Obviously, the systems have been very rapidly improving the quality of what they call the chaperone system, or typically called chaperone systems, the sort of virtual walls around you, but you don't know how much space you're going to get. You don't know its configuration. And so you'll see that certain games have different sizes. They have a minimum size of space. A game like Unseen Diplomacy has to have a fairly large space to start off with. But others just demand that you have, work in sitting mode or standing mode, and they actually switch between the two. More interesting, some games they can adapt to the space you've got. And for example, a job simulator can adapt to the size you've got. It has different size spaces. So this is critical for consumer VR systems. They've got to work. And I thoroughly remember some early demos, in particular I think I remember playing the lab where I couldn't do one of the demos because I simply couldn't reach one of the objects, and there wasn't a way of moving. Right, so if you go into one of the demos and you happen to start in the wrong place, you won't be able to reach some of the objects. Now you can add tools to your system to allow you to do that, but they're very much specialist tools. The third thing is that they need to be, any consumer VR application needs to be very accessible, because there's a lot of it's got to be pick up and play. Tutorials have to be straightforward, and again in the lab and a lot of the work we're assuming that somebody can explain the system to them, hands-on, dealing with the interface, showing them how to put things on. And we've got devices, I don't mean to disparage it, but we've got a Dexmo glove in our lab, which is a hand robot that you put on the outside of your hand. And it's expensive and it's targeted at labs, but you can see that in a consumer situation, there's me always picking up my Oculus Quest controller wrong. That's going to be a difficult thing, and it needs somebody to help you. It needs you how to explain how to use it, how to calibrate. So yes, I mean, very much the expectation in the consumer world is that you can pick it up and play it, and it should be self-explanatory. And that just is a lot of work, right? A lot of the techniques are simple, not too many options, not too many parameters, just because lots of people need to use them. And they'll skip through tutorials if they can. And the final sort of framing is that it needs to be failure cases. So again, when we develop things for 3D user interface controls, and I've been guilty of this in my experiments, that there's always a safe mode for the experiment. We can reset it. If something untoward happens, then we can fix it. So, for example, in one of our own experiments recently, we've had a sort of shopping. We've got a supermarket and we've got a conveyor belt, and objects move along the conveyor belt. It's supposed to be easy. You're supposed to pick up objects and scan them, and they beep, and then you put them on the side, and then the number of ways this can go wrong will boggles the mind. To be honest, it's a sort of people pick up the objects, they manage to push them through the table, even though that's not supposed to be possible, but it turned out there's two collision volumes next to each other. What happens if they drop it out of sight? What happens if the tracking system has a bit of a moment and decides to fly off to the other side of the room? And all of these things in a consumer app, they have to be defensible. You can't have an object disappear out of the collision volume. There's got to be a way of getting around that. And so in these consumer systems, you have to plan. You have to have fallback positions. It has to be able to detect its state, and therefore that restricts some interaction techniques. There are some things you don't do because they're hard to recover from. Okay, so having framed that, what do we do? So the main question is, what can we learn from all of these consumer VR applications? So those tell you some of their important criteria, design constraints, some of the things they're thinking about. So that's already a difference that's interesting, but what can we learn from them from what they've done? And so what we did in this work was we looked for specific sort of interesting techniques that could be realized that deserve further study, essentially. Things that a group of us thought were cool, interesting, solved a particular problem in an interesting way, probably ideas, things that we could use, and ideas that we wish you'd had before and written up as papers for conferences. So what we did was obviously, as I said at the beginning, there are 6,000 applications out there. It's almost impossible to sort of, and that's only applications, right? There are hundreds of demos. There are applications that have come and gone. That are no longer available. They may have been for Gear VR, for example, and therefore they're not available anymore. Developers take them, stop selling them. They just don't want to deal with users anymore. Also, some of them are just built for specific installations. So we crowdsourced this. Well, mainly led by myself with Rob Lindeman's help, and we like to thank Cal Johnson, who has an interest in VR games, and we sort of crowdsourced. We put it on some lists. I posted it on some private developer forums for game developers. I'm afraid they're invite only, so I can't share those. And all the materials, including papers, LaTeX, BibTeX, PowerPoints are all on this. It's completely open, and the idea is that we'd love to encourage people to carry on with this spirit of trying to find crowdsource and open source examples. So in particular, if you go to that URL, you'll see this website. I'm afraid it's a bit dormant at the moment. It sort of needs a new champion. I'm unfortunately very busy because I've got quite senior in my department, and I'm helping with planning a new building. But the idea is that on here, you've got lots of examples of things that people think are interesting. And this ranges from the authors of the paper and also just suggestions that came from some PhD students. And I should say that the authors of the paper are sort of self-selecting in that we did a lot of work or nominated ourselves to actually write up the paper. But there's a version 2 to be done if anybody fancies getting involved and championing it and gathering some more suggestions. So in the paper, there's 20 suggestions. I'm going to talk. I will talk, depending on time, for about somewhere roughly 10 of the suggestions that are in the paper. There are 19 other ones in the Trello, which we didn't make it into the paper because it was too long. Well, it would have been too long, but there's a second volume in there to be had. And there's some more discussion, supporting discussion to be had on the online, for example, what really is it? Are we trying to isolate from this rather than just cool stuff? And there's some reflection to be had on the crowdsourcing process. If we've been asked, couldn't you do that for AR games, or how about novel devices in games? And it would be different, but of course it would be great. I'm afraid I can't lead an effort like that at the moment. Okay, so let's just, so in the remaining time, let's just talk about some of the suggestions. So, and because they're commercial products, they're easy to find online. There's a lot of videos. So on the Trello board, there's some source material for each of these, but in the paper and in this talk, because these are commercial packages, and I don't. We're going to use cartoons that we drew for the paper. So this is anything else to say? Yes, and you can find links to videos of some of the things online. And for each example, we've tried to find multiple sources. One thing we didn't do, which we did have a long discussion about, is trying to find if there is an academic paper that suggests the same idea, do we cite it? That we also discovered was going to take a very long time, and so we found sources when we can, and if anybody wants to propose a source, it'd be great. Please add it to Trello or email it to me. And in some cases, that will be very valuable for other people to know about. Anyway, to press on with the examples. So the first one that we highlighted, we split them down into the sort of main, the sort of big categories that people have proposed in the 3D UI literature. So selection, manipulation, travel techniques, and then system control. And to some extent, many of you won't be surprised by examples, right? So what we're going to try and do is, I will try and do is point out what's interesting about these examples. So the first one is intention preservation. And this is about the example game that we identified here was the bullet train. So in this game, they do selection of objects. So selecting which object you want to pick up in a very interesting way. So if you haven't played the game, if you search for it on YouTube, you'll find dozens of videos, hundreds of videos of a very fast-paced game. You have to pick up guns. You have to pick up the gun and then shoot it, and things happen in slow motion, and it's very dynamic. It's free, so you can play it yourself. And interestingly, when we think about selection techniques as they were described in the literature, there's the classic ones are eye, hand, ray, which is labeled by D in this figure. So blue things are the sort of head-mounted display. What the physical devices, the green things are the user, the interaction things, and anything in gray is the sort of background. It's easier to follow the cartoons and watch some of the videos. So eye ray labeled by B. So the direction of the gaze labeled by D. The direction of the gaze through my hand labeled by A. The direction where I'm pointing labeled by C. And they don't use any of those. Right, so they don't use any of those, any of those three choices, which are the ones that you can get in the book. And interestingly, they said the reason for this is that it doesn't do what people intend. And so what they did is actually find another vector that's sort of halfway between where I'm pointing and where I'm looking through my hand. So in my situation, it's very difficult to mime, easier in person. Let me do it from the side. So instead of this vector or that vector, it's that vector. Okay, and they said that this is more likely to be right in their testing. They said it was more likely to be right, and so we've assumed that they split the angle. The actual source for this piece of information is actually a talk at GDC where the developers talk about how they implemented it. And so that's really interesting because that's that's amenable to an experiment. That's one of the purposes of the paper. Let's find some experiments for students to do. Yes, so that do you do it where they point through the hand or halfway in between the two? And I think the key thing there is speed. So the person here is not always looking at their hand, right? They might look at the target, point, and shoot, but there's so much going on that it'd be really interesting to see if this depends on which direction they are looking and how fast the action is. The second one. So this shouldn't work. right? So the whole game is a bit of a bit of an outlier. Res Infinite, Res is one of my favorite games. I do like the games. I don't get that much time to play them at the moment. But Res Infinite is definitely worth an investment. I've actually bought 3 copies of this now for different platforms, because it's I just think it's fantastic. But in Res Infinite, if I explain the paper, the picture, you have to aim at things flying towards you or flying past you. The other thing which is unusual about this game is its constant movement, and the camera's moving around. So there's another aspect of this game which is really interesting. But there's a cursor on screen, and you have to select objects as they fly past, which is the green thing in this game. This is what you're controlling. But both your head and your hand move the cursor. So if you keep your hand stationary and move the head, it's a slave to your head, and so it's effectively slave to both of them, and it sets up a rotational coordinate system around you, which is really fast. So that's interesting. Again, because it's nothing that possibly anybody on this Zoom would have come up with. And it's very effective. So you can turn it on and off. There's an experiment waiting to be run, which is, can somebody learn how to do it fast with both? You can do it in either or both, either one or the other or both. And it would be interesting to see. I don't know, maybe the game developers themselves have the statistics. I should write to them and ask them which mode of the game is actually most effective. But again, it's fast-paced environment. It's mostly selection at a distance around you, with ray selection, so not proximate selection. So that might be applicable in many sort of scientific visualization contexts, for example. Okay, tomato presents. So this one is one of my, again, another famous game. This is the game Job Simulator. This one, I keep wondering whether or not we should have put in the paper, because I keep running experiments on this. And so I've run 3 experiments on this and not managed to write up any of them because the results are confusing. And it's based on so my attitude to this is based on the rubber hand illusion. So we've shown that sort of ownership of the body in VR experiments. Many authors have. So the idea that as you're in VR, you've got your hands, you see them, as you move them through the space, you start to own them somehow. And in particular, one of the things that we've done and others have done is threaten the hand. And you threaten the hand, and somebody feels as if you're threatening them, even though what you're doing is hardly any damage to any polygons, never mind your actual hands. So great. So here's that's one of the what I see, one of VR's great theories, body ownership change. And if you're interested in that, I would just refer you to any of Mel Slater's recent work to see really how rich that field is, and how you can use it. Job Simulator, on the other hand, basically says rubbish, right? So it's all rubbish. Body ownership is not important, because when you pick up an object in Job Simulator, your hand disappears. So this is the sequence of the things in the cartoon, and you reach out, you pick up the sugar, your hand disappears, your hand is the sugar, you move the sugar around, and it's not important. Okay, so why does this work? So we've tried running rubber hand ownership illusions on this and haven't found, we've got results which aren't really reliable enough to say very much. It's obviously just very, very difficult to do. This is the supermarket, right? Remember the supermarket, I mentioned a supermarket counter. That's the experiment. We've found it's complicated. Anyway, so this is really interesting. It suggests something which is a gut feeling which I've had for a while, which is it doesn't really matter what your hand looks like if you're doing something. It just matters that the sensor motor match is there. So your hand turns into a sugar jar. The sugar's there, it's not disappeared, it's your hand disappeared, but it's the sugar you're operating on. So it's the sugar you want to move. So your hand is then immaterial to the sugar moving, and you still see the match between your hand and the vision. So that's really interesting, but there's something there. about what is happening to the body ownership there. If body ownership is so important to VR, what's happening? Is it if you threaten the sugar, would you react? And yeah, that's a great question. If anybody wants to work on that, I would be very happy to work with you. Okay, a simpler one. So I mentioned at the beginning that the idea that you could not have enough space. So this is an interesting technique. It's sort of obvious, and probably we almost implemented this in demos in the past. Not quite, not exactly the same thing. I'm sure people have in experiments over the years. There's the idea that when you drop an object, it just goes back to where you remember it. So in the lab, inside the game, the lab, which is the demo with Steam VR, there's a horde shooter game called called Longbow Tower Defense, where you pick up a bow and you shoot arrows, and there's a fire over on your left, and you can set fire to the arrow, so it causes more damage to the little creatures that you're shooting. But if you drop the bow, it doesn't fall. This is the physics thing. You don't want it to fall and disappear or potentially head through a collision volume. It falls and then it just goes back to where it should be. Right, so you can manipulate it. You can put it. I believe you can put it down. I would need to check, and then change hand, for example. But if you let it go for more than a few seconds, it just reappears in the place where you expect it to be. And that does mean that you don't lose it. Again, this is a very fast-paced game, very important piece of gameplay to be able to pull arrows really, really quickly. But occasionally, if you're using this on Vive, occasionally, the hand gets stuck, and you might. I've played this game and my hands got stuck. And you might let go, and then you get the bow back again because you want to wave your hand around into the place where the tracking works. If you're using something like the HTC Vive. That's great. Interesting questions here, for example, would be how many of these can you reliably access in the local space? Is this like, can you learn to use a dozen, 2 dozen? Can you make up your own interesting space to have tools in it? And of course, there's lots of interesting ideas there. Okay, this one is one that actually came from academia, but is used quite effectively in some games. Again, it's one of these ideas in virtual reality that is a little bit scary for those of us who've been around for a while. The game Eagle Flight has you flying around like an eagle, sort of banking and turning. And again, that's a sort of visual flow which doesn't match to your visual proprioception, sorry, the vision doesn't match your proprioception, and so it's not clear if this is going to be nauseating or not, but by sort of the narrow field of view narrows when you turn, and therefore it's well, at least that game could ship. I don't know if the people are if they are still having simulated sickness with that. Obviously, I think it's Ubisoft that did it. Somebody can correct me in the chat, I expect. So they're a big game company that needs to be careful if they're shipping games to large numbers of consumers in case of either harm caused or just bad reviews. So that's really interesting. Of course, it was described in the literature, and this effect of narrowing the field of view is understood to decrease simulated sickness. Though there are some subtle differences to the consumer system. So, for example, if many of your users are sat down, then obviously most of the work on simulated sickness is assuming that there isn't a sort of body reference through your backside for the simulated cue. So maybe that's sufficient, and is why we're not seeing so much simulated sickness. Thank you, Ubisoft. Yes. Yeah. Interaction scale adjustment. So this is an interesting technique. A few games have it. We're just showing a cartoon from the game The Spy Shrunk Me. The reason for mentioning this is as a technique is that people have avoided it somewhat in the sort of experimental work. A notable section being a paper that, again, self publicity. Well, it was done. Sorry, the first author's name just escaped me, but it's the paper done at Microsoft while I was there. I'm going to have to look it up. Apologies for this. I did. I'm a Giant, Parastu, about it, from who was an intern at the time. Let me just post the URL into chat so you can look at this. So this is a paper that interested. This paper is a sort of interesting paper by Mar Gonzalez-Franco and I, and Parastu Abati is the person's name. I'm sorry, I was on the tip of my tongue when I couldn't bring it out. And Ilofek and I happened again when I was on sabbatical. There's a nice tie in there about people's interpretations of different scale in virtual reality. There are a few games that do this, use different scales, and we could look at there's lots to do here about how people interpret change of scale, how to infect it accurately, and then their impressions of being at different scales. So that's really interesting, and this is something which is on my my standard sort of student project suggestion list. Okay, now we've moved into sort of travel techniques. Then, of course, the teleportation has sort of taken over the universe in consumer VR games. Obviously, it's not completely dominant. Many games have an option of both. For example, my team and I spend quite a lot of time in Rec Room just for socializing. And although teleportation is the default, there are certain, if you're going to play Laser Quest or Paintball, you really want to have the joystick on. So although I hate having the joystick on, it's just more fun playing that particular sub game with the joystick, even though if you play it for too long, I start feeling nauseous. And despite my career in VR, I still don't have VR legs, and joysticks easily. A badly implemented joystick will make me ill. But there's lots of variations on teleportation. There's lots and lots of variants. Like for example, I previously mentioned sorry, it's quite late here. My memory's going. Back. This one, Bullet Train. I was calling Buffer Zone for some reason. My head was going Buffer Zone. Bullet Train, which when you teleport around, it actually puts you in a specific place. And actually, one of the confusing things about the game is you actually can turn all the way around when you teleport. You get to say where you're going, but the orientation is chosen by the developer. So that's a little disorientating. Mostly when you teleport and you're facing the same direction. Just to put into the Room VR, as I mentioned, as an interesting test case, not only because it's a good game, but it actually switches between the two. So you can play it sat down or you can play it stood up. And if you play it sat down, it does the sort of turning thing, but it does it subtly. So you never get turned all the way around. It's usually only a few degrees. And you can see that this is actually right near the start of the game. If you're sat down and you teleport into the room, you could see that it changes you from the main line into the direction shown by the arrow, which is not a lot of change. And actually it does that to just help you so that you're not you're not then sat at this, sat off to your side. If you're stood up, it's just position-based teleportation. So that's really nice interface. And I'd played that both sat down and stood up and hadn't noticed the difference until somebody pointed it out to me. That's really subtle. Really interesting questions there about the impact of that technique and on efficiency, and just did somebody, I didn't notice, does anybody notice these subtle changes that sort of help your effectiveness in the game? There's many elaborations. So just rotation teleportation in Half-Life Alyx. Not everybody uses this, but you can turn the feet as you teleport. So you can, if you've got a joystick and you can turn it, you can do that in all sorts of ways. With the joystick here, we've cheated a little bit. This is the Oculus controller, not the Vive controller, but you can play it on Oculus with the right tools, and you can move the feet around, and therefore you set which way you're going to face when you teleport. Okay, did one go missing? Preview teleportation. That got out of date, out of order. Preview teleportation, one I'm really interested in at the moment. One of the arguments about teleportation, again, we've covered in our own work, is what do you miss when you teleport, about the spatial orientation. And here in the game Budget Cuts, as you teleport, you get a sort of preview of teleportation. That's very important for the game later on, because you're going to teleport to places you can't see, and that's part of the strategy of the game, so you can see what the creative minds at work there. And you can teleport through things, through vents. That's not a big hint. Well, actually, that is a bit of a spoiler for the first sort of puzzle in the game, one of the first few puzzles in the game. But it's really interesting because what should the preview look like? And there have been people already that have looked at this. But I think that's very usable technique in a lot of different applications, because teleportation is sometimes hard. I mean, obviously, most games are sort of in real environments. I'm thinking about applications which are more abstract, sort of data visualizations and so on. If you teleport here, are you actually going to get to the place that you expect to be? And can you configure it appropriately? Okay, that one appeared twice, that's why. Body-centered menus. So here is a really interesting example. Again, body-centered menus, nothing that anybody wouldn't have presented in early literature. The idea of having a menu slaved back to your body goes back to Mark Minay, I expect, and his early thesis on sort of space and object referencing that's around the body. We've built tool belts in VR. I've implemented one. We've implemented menus that come to hand. This one is in Lone Echo as just a particularly good implementation of that. So menus stay attached to your body. And to some extent, one of the ways to think about that is it's a VR interface, which is basically many sci-fi augmented reality interfaces. It's near you, it's proximate, it's personal. And that's really interesting. An interesting way forward, and you can see lots of examples in different apps, and everybody's got good examples of that. This one bit about menu control is worth a whole survey on its own, because there are very different ways of doing it, and it'd be interesting to look at effectiveness of this type of interface versus more what you might call dyadic interfaces, which are always in the world. So there are objects in the world that do things, but yeah, compared to things which are sort of floating and brought to you or looking like menus, 3D floating menus. Okay, and then the very final one, I think, independent visual background. So again, this is something which is understood, but it's now been picked up in many games, that if you can explain movement with a visual background, then it'll help people understand their position and will make them less ill. Okay. Right, just to wrap up and give you a couple more final thoughts. We're not claiming that these are new. They're just good examples, right? So there's lots more to deconstruct. They're sometimes implemented in many games. There's still hardly any conventions coming out. That's where academics can help and our research can help, is enhancing these, settling arguments about one or the other, or just improving knowledge about, say, scale changes and so on. But in conclusion, it's sort of, we've tried to make this a bridge between the varied imaginative design in consumer VR applications and the sort of academic community. And I hope you found that interesting. If you've got any comments, especially on the relationship to novel devices, I'd be very happy to answer them. And of course, this was an open process. We'd be very happy to help with anybody that wants to focus on a particular area or expand this type of work to look at more consumer VR applications. Thanks.
Very much, Anthony. That was a really good keynote speech. Thanks a lot. So before going to my questions and my comments on this, are there any questions from the audience? I'm looking at the Discord. I don't see. Discord has a question. Yeah, please go on.
Thank you for the great presentation, first of all. One thing I thought about was the combination of different movement types and user interfaces. Like, have you looked into that, and if there is?
That is an excellent observation, and one of the things that we gave up trying to think about in the paper. But yes, there's an obvious thing here, which again, not well done in academia, but if you pick one selection technique, you sort of get an implicit manipulation technique. But if you have a manipulation technique, how does that constrain your travel technique? So people have talked about differences between ray and hand selection as being important if you want to carry an object through the environments, you want to carry and travel. So how do you manage that? So obviously designers of any of these games have had to think that through, because of course they've got to. The one thing about the game, as I mentioned, is it's got to be finishable, and you can't get into a situation where you get to a dead end because you can't pick up that object and move through that door because you didn't have the collision detections. So yes, there is something to be done there. I just think it's an excellent idea. I don't have much to say apart from, yes, the combinations are really interesting. And at the moment, it's dictated by the games developers more by the sort of story and metaphor than it is by the raw sort of input. So you might then see I expect you'd see them use a less than optimal technique because it fits with the story. Or they've had to fall out of their story to their sort of metaphor to make it work. I'll give you one example, which is we have talked about in the past. The game I Expect You to Die is a SAT experience where you're a spy and you have to solve James Bond-like puzzles to avoid being shot. Okay, so it's a lovely game, well worth. There's lots of very, very interesting design ideas in it, and it's a very in-room idea. The idea everything's within reach, and you're just manipulating. You start off in a car, and you can reach everything in the car. So if you want to get something from the glove box, you have to reach over. Except this fails because things go out of reach, and when they go out of reach, you can't see them. So they actually go transparent and they stop. So if you drop something behind something, you can actually pick it up at a distance. So it's sort of, you can see that they've stretched a metaphor there, and they've had to choose a selection technique that possibly wasn't quite the one they wanted, because it doesn't. And I think you can see a few examples of that in games that there's been a compromise in the selection technique. Maybe there is another idea that will come to them now because they've seen many more examples. Yeah, combinations are a good problem, and the combination of menus and interaction is another great problem. I mean, I will pick on Rec Room because it's so popular, but they've got two different menu systems at the moment, and they just clash, right? So they went from a sort of I forgot what the term is. Sorry, it's quite late. Semi sort of realistic 3D buttons you push in and push out to something which is 2D and flat, and I'm forever accidentally pressing buttons on it now. But they must know this because I must get complained about all the time. So again, they've made a compromise in going from very sort of it's a tray of buttons and to another one, and they clash in the same menu system, unfortunately.
Yeah, thank you for the excellent answer.
Okay. The question.
Wait, sorry, I was muted. Any other questions from the audience? No. And there are also no other questions from Discord. I have several ones. The first one is, I really like your approach in terms of getting in touch with the Hood design, and I was quite fascinated that when we were conducting the different grip styles experiment, I realized that actually the consumers find different solutions to games. For example, in the Beat Saber game, they invited new the grip styles that doesn't exist, like the close grip and like beer grip. They were really different, and which they improved. They claim that it improves their in terms of their points. They were able to achieve the levels, and when I tried that in the different songs, they actually work. They actually work better. And I was thinking like as a community, as a VR community, and as VR researchers, what we can, aside from that, the people who design these games, what can we learn from the consumers, that the players by themselves, because they are trying to cheat the game. They are trying to find kind of like a new feature. And when they're, for example, motor performance, when there's a limit, they are trying to achieve that with finding another solution.
Well, the first thing we learn is that gamers are very motivated. So very motivated, and as we know, they'll buy faster PCs to optimize their gameplay. And you might have noticed in the last week that NVIDIA's had a new round of it. I forgot what it's called. It's low latency esports monitors was released last week at 360 hertz, which is pretty ridiculous frame rates. We haven't got one yet. We are getting one, and we'll of course test it, because we think they're upsampling the frames. So yes, they're very motivated, and yeah, I love that picture. There's if you want to Google it, maybe somebody can find it and post on the chat. It's delightful, right? There's a picture of because their grips are different for Oculus and Vive, right? And in the Vive, they reattach the strap and wrap it around your hands so it doesn't fly off and things like that. Also, another really interesting thing there is the handicapping system. Right, so you can play the game with more handicaps to make it more interesting for you. So the game space is very, that game has done a good job. It's popular because it's pliable. I think that's one thing we can learn. That it's actually quite, it's quite editable, lots of features, different speeds, different. So that's that. And when you're optimizing it, players are actually optimizing the game for their skill as well. So that's another thing to learn. They're motivated. They're very interested in modifying and changing the user interaction techniques. Cheating. So yeah, so cheating is an interesting one. I would say the opposite side, the flip side of cheating is accessibility. And so I look at some of the stuff that's done in Beat Saber and go, that's great accessibility for somebody with limited movement. So if you're going to stick your controller on a stick, great. That means you can play it without moving so far. So I think, yes, that's interesting. And also another observation, and I'll stop because I think it's we could debate this for ages, is that what we're seeing is the people reimagining the use of the controller. So we often think about the controller as, well, this is just a proxy for your hand, and we know what hands do, but Beat Saber it's not my hand, it's something that moves fast in the right direction, and that's been seen before, right? So there's a really interesting case study of a game. I will look it up and post it to Discord on Nintendo Wii, where they discovered that the game was too easy to cheat on the game because it was a sword fighting game, and it was too easy to make micro gestures that beat the game. And so there's an interesting discussion at the Develop conference, which is a game developer conference in the UK, where I went to a talk and they talked about how they made sure that people had to make relatively large gestures, but not too large, because then the adults wouldn't play it because they would too much effort. So that's really interesting. They're thinking about the controller to then optimize for the actions, not what we think you're going to use your body. So yeah, we're stuck with the controllers, and there will be a really big difference between hands-free and controller-based games. So I'm expecting quite a lot of very significant difference in game design for hands controllers. It won't be easy to port most games to it to start off with, but I think you'll see Beat Saber won't work if you have to. Well, it might work. Somebody will make a variant, but you can't do this, right? I mean, maybe Fruit Ninja will work, but Beat Saber will not work.
Okay.
I'll put money on it. Anybody wants to? We're not supposed to open books on this at workshops.
Yeah, but,
that's encouraging students to gamble, but I'll probably take bets on that.
We have a question from Caroline. Caroline, yes, she's gone.
Hi.
We cannot hear you, Caroline. No.
It doesn't say you're muted, but we can't hear you.
Can you hear me now?
Yes, we can hear you.
Okay,
Yes.
Great. So I was wondering if you gained any insights into how consumer VR controllers create haptic sensations, because the controllers, of course, have certain limitations, and we know from academia, for example, that you can induce pseudo-haptic illusions using the virtual cues. So visual cues, sorry. So I was wondering how consumer VR applications try to handle those limitations, and if they use those pseudo-haptic effects that we know from academia.
Yes, they've all got the vibrotactile feedback, and I haven't seen much. Again, this is out of the scope of the survey we did, but it would be fascinating to probe further how they're using feedback on grasp and so on, because of course it's a relatively slow cue. So you might want to do it in anticipation. The buttons are usually capacitive, so you might anticipate feedback and so on. I think so. This is an area where I think there is a lot to learn from the academic work, and there's a device which I tried when I was at Microsoft called the passive claw, where they're sort of playing with this idea of something that a controller that appears to change size when you vibrate it in certain ways. It's a sort of generalization of the tactic illusion that Apple uses on its keypad. So I can't say I've seen anything in games. I'll be really interested if you had, or anybody else had seen some interesting illusions there. I do know that Mar Gonzalez, before I was at Microsoft, but he has an interesting paper on a version of the cutaneous rabbit illusion, but using VR controllers. So that's really interesting. But you have to tie the two controllers together, which obviously to get that illusion. But maybe somebody can make that work. So the cutaneous rabbit illusion, I'm just writing a lecture on this, by the way, is the illusion that you tap frequently here and then here, and if you do that fast enough, you perceive a sort of series of taps along your arm. If you do it right, and she made it work with two controllers with the stick, that you vibrate one and then the other, and that you could feel it. You feel as if it moved along the stick. But there's lots of things you could do. That's one where we could write a paper on things you could learn from us in response to put in new controllers.
Yeah. Maybe a second question: do you feel like it's a focus in consumer VR applications that they are trying to incorporate more haptic sensations, or are they just maybe?
They're a bit limited at the moment, and I think we'll come back on this lowest common denominator problem again. It's a sort of even between games controllers. I believe, I might be out of date, that the PlayStation 5 vibrotactile has more dimensions than the Xbox, probably because Sony has the patents. So then, of course, it's a case of, well, do you put the effort in for one controller or none? So I think at the moment, vibrotactile is very primitive, and I think we'll be stuck in the Quest 2 is the lowest common denominator, and you'll see some developers showcase their device for new ones, but I don't think, maybe somebody else would know if any of the VR controllers have more than one motor in them, but I don't think they do. But lots of illusions that you can do with vibrotactile, so some very promising.
Okay, thank you.
Thanks, Carolyn, for the question. Are there any other questions that? No, no, there are no more questions. I just want to get your comment on one last thing. I'm just going to stop here. So we're just going to give like a 10 minutes break. Really short question about, I recently played the game called Wanderer. And one of the things that I really, I wish there was is, I mean, for the people who don't know the Wanderer, it's the game like you solve the, it's like the escape room games that you are trying to solve the puzzles and you're trying to get out. One of the things that I wish there was is the precise interaction with the objects or the placing them, and that was missing. For example, that was, I mean, I don't know if they taught, but I also feel like there's a gap in terms of the developers having ideas from the researchers. It's not only from one side to other, from the other side to us. I mean, that as developers, that there is a gap between that. And what do you think that how we can close this gap?
So I think some of them do pay attention to the academic conferences, but yes, it's a good question. We obviously see their results because we play them, and I have found in a couple of instances we're doing something very interesting at the moment with an actual game developer. We've just written to them and said, look, we like this, but how about it was like this instead? And they've said, okay, yeah, that's really interesting. Here's a GitHub repository, which of course caused some stress trying to build it usually includes installing another version of Unity. But yeah, I think reaching out, and if you've got something specific idea, then many of them are small developers, indie developers that are happy to talk to you about it directly. And they're more used to, even compared to 5 years ago, engaging with their audience on Discord. They might not have any time for you, they might not want to share code, but they're happy to chat with you about it, and they may even be able to tell you why they didn't do a certain thing. I certainly, in a couple of instances in the chat leading up to the paper I've talked about, we had some insight into how the decision processes were made. Yeah, but I think no harm in reaching out to them. Or training up students and sending them out into the world to do the deed on your behalf. Great,
perfect. Thanks for the talk, Anthony. That was really good. All the work you uploaded. We are just gonna give a break, and in the just let me share my screen. Yeah, we had this. Yeah, now that we're just gonna give break until 13:10, and then we're gonna continue. I think we can start for the panel discussion. So just to be sure, Wolfgang, are you here? Amy, are you here? Anthony, are you here?
Yes, I'm
Wolfgang
here.
is here.
Yes.
Amy is here. Anthony? I think Anthony just give a short break after 1 hour of the keynote speech, but yeah, that's something that I'm expecting. I'm just gonna go briefly until actually, let's wait like a 1 or 2 minutes and then we can start until the Anthony comes here. Anthony, are you here?
Yes.
Yeah, perfect. Then we can start. So again, hello everyone. Thanks for coming to our panel discussion. We have 3 really perfect, good researchers and our keynote speakers, the previous keynote speakers here this time. Amy came to NIDIT 2021 as a keynote speaker, which was last year. Wolfgang was our keynote speaker in 2019, and Anthony is today that he was our keynote speaker, and we asked them to come together and talk about both what they did in the previous years and what they're planning for the future, and have a short panel discussion about the input devices and the interaction technologies. So instead of showing these questions, I just want to close this screen share so that will be even easier for people to discuss and to see them each other. So I can ask directly my questions. So I'm going to start with my first question. Let's start with the Amy. Amy, what were you planning for your research when you gave the keynote speech in NIDIT, and did it change any way that in any way from what you had in your mind?
Yes, thank you. I'd like to go ahead and share my screen. I did prepare slides.
Oh, that's good.
Okay, so can you see that okay?
Yes.
Yeah, so in 2021, I was doing I had finished up a portion of my sabbatical at CU Boulder Atlas Institute. And I was working on a number of different methods of input, and one being kind of exploring silicone volumes for input. The other is we were calling kinetic skin, where we were setting up a temporary tattoo that you could wear on various joints of your body to then track relative change in angle of your joints. And the other project we were working on was exploring how you could simulate vertical ascension and descension of stairs. So how could you manipulate the view of the environment or other aspects relating to your head view and objects in the environment to then allow you to perceive stair climbing and allow you to also feel the exertion that you feel when you're going upstairs. And so we're looking at a number of different conditions related to that. And one of the things, part of that question that you asked, so how did COVID-19 kind of change what we were working on? Part of it was that since we were using the formal laboratory setting, we were using props in the lab, made it a little difficult to do it in the lab once COVID-19 prevented us from kind of being together in person. And so that was one of our biggest challenges, and simply delayed the project for us to collect data for results. And I know a number of researchers are doing an amazing job of kind of doing virtual studies and kind of, and I think that's a really great way to go. But there was something that we didn't do for this project, and so it simply delayed. And at the time, in the keynote presentation I gave, I kind of outlined several challenges that I was thinking about at the time, and what we might look at. And so in preparing for this, I was kind of reflecting back on some of the things that I was thinking about and where we're at now. And one of them was kind of augmenting 2D communication methods. And I still think this is an interesting challenge to look at, where how can we increase co-presence across non-immersive platforms? So if we think about, even in this VR conference where we're doing the presentations here in Zoom and not in the virtual world, my question is either why or how can we increase co-presence across these kind of platforms? So I think that's interesting to look at, and a number of people are kind of looking at some of these things and how to increase hybrid interaction across mobile devices, desktop computers, head-mounted displays, and just kind of increase the flexibility at which we kind of join or network with each other, connect. And so that kind of goes hand in hand with looking at how we can integrate those off-the-shelf products more seamlessly, or having those available. Another challenges that I was reflecting back on was this idea of how do we transition from this post-pandemic culture, conflict and shock. And was interesting, I was talking with a colleague that they were kind of interviewing students for PhD candidates and things like that. And one of the things that was said to me was, I think in this interview process, people have changed a little bit in how they interact in person. And I think that's interesting. And it's, can we use VR environments to then train people in various social skills, or how do we bring individuals kind of back into this real world, if you will, and how do we look at what has changed with the population. So do some of the past studies still hold true with our new population? So that's an interesting question to me. And then another challenge is kind of related to what was talked about in a little bit, is this idea of kind of looking beyond the visual. We need more augmentation of the senses, so haptic, and even if that's in the form of pseudo haptics and illusions, I think ways that we can kind of get beyond just that, you know, VR is not just visual, and to make it more accessible to those who do not have that visual channel. And I think that is important to look at. And then, so this kind of ties into what I was saying, in that with this type of environment, kind of looking at Zoom offering capabilities, both, you know, flexibility and accessibility, I think we should increase the understanding of those and how we provide those for VR environments. And then the last one was that virtual simulation. Can you understand enough from conducting virtual evaluations, not in the physical world, and can they transition to or apply to the real world? And I think there are a number of researchers working on this, and presentations that I see slated for this week. And so I'm really excited to learn more about what our community has done in that regard. So I'll stop there. You're muted, Anil.
I'm asking Wolfgang now your turn, and he's not answering. I'm like, why is he not answering me? Wolfgang, so what were you planning for your research when you gave the keynote speech in NIDIT, and did it change in any way from what you had in your mind?
Okay, now that I know what the question is, sorry. So I'm a little bit different position as most of the other people on the panel, because I gave my keynote 2019. That's well before COVID. So at that time, I would basically say, well, I was planning to do business as usual, right? Do a lot of research projects, and quite a few of them have appeared in the meantime. So in that sense, when I gave the keynote, there was no big change for me. However, I mean, as we all know, things changed rapidly, right? So and as Anthony know, in the beginning of 2020, I was actually visiting Anthony in London, and thank you, Anthony. And it was a great visit, except that COVID made it necessary for me to bail on the sabbatical visit, right? And that was fun, because, you know, I flew out like 2 days before Canada closed down for incoming flights. So that was interesting. Now, really what changed was that we had to restructure a lot of research at that time, right? I mean, in fact, I mean, it's interesting to reflect back, and when you ask these questions to answer, one of the things that I realized is what changed so much is not what we did, but how we did it, right? A lot of the projects moved into students' homes, right? I mean, no surprise there. But I'm also saying we were lucky. We as a field, and also my lab, because we were able to do that, right? Head mount displays and the computing hardware that was required was already advanced enough and portable enough that you could do that, right? If I think back for some of the tracking systems that we used, say 10 years ago, that would have been a lot harder, okay? So one of the things that made me realize this change was we got lucky, right? We were just technologically advanced enough that we could do continue some of the things, because our university closed down, right? Basically, right? I mean, we couldn't get into the lab for a while. getting ethics approval to run experiments. I mean, I remember that it took me like 3 months to write a site safety plan, what we called it, that allowed us to go back into the lab, right? That just allowed us to get back into the lab, right? And to think about running participants again, which then also didn't happen because of under changes, but it was like a huge change, right? And so by having the ability to have hardware at home, that made a big difference. One of the things it also made me realize is, while it seemed very attractive in the beginning that everybody could be at home and everybody could have their hardware at home, we as a community in the lab realized that we were missing a lot of the connections, right? The chat that you had when you're in the hallway or when you walk by somebody else's desk or whatever, all of that got lost. So I think it is fair to say that there was an impact that has nothing to do with technology. It's just a social loss, basically, right? And that is something that I want to highlight, because you actually realize it only afterwards, right? I mean, you see today Microsoft going back and various other big companies basically calling all employees back, right? And the only explanation that I really have is, well, they're realizing the value of the social loss, and that the same thing applies for research labs, right? And hey, I'm also going like, well, no, it's easier if I don't have to commute. I agree, right? But there is a cost, right? So that's also one thing that that kind of occurred. In terms of research directions, because some of the questions were around that, not that much has changed. One thing that it has really put into the forefront is that all research that uses additional hardware, like say Amy's tattoos or something like that, or some of the things that we build in my lab, the controller, the various controller things that you do where you build add-ons for things, or you build a new display system like Ufuk, you did, right? When Ufuk was in my lab, right? These things were harder, a lot harder during the pandemic, right? And sometimes almost impossible to pull off. But I'll stop here for now.
Gang, just a side note, when the COVID started, when Wolfgang was in sabbatical in Anthony's lab, I was the only person in the lab in terms of everybody was, asking things, and I wasn't even an assistant professor. I didn't know anything, and there were lots of fires to distinguish, and that was terrible. That was a really bad experience.
And I want to publicly thank Ufuk for helping out here. You saved a couple of research projects there, Ufuk.
Okay, Anthony, I know that that you just gave a keynote speech, but in terms of when you go back to 2019, 2020, before the COVID time, what were you planning for your research when you gave the in terms of when you had to, if you had to give the keynote speech, and what changed in your mind since pre-COVID?
So I also did a few slides that sort of address this, but I'll try and address more of the question, because so to some extent we were trying to work more with consumer content for a long time now, and for a couple of reasons. One is just recruiting more users, getting a bigger set of users, also publicity, and sharing ideas. So we've had this we did an experiment, and it was in TVCG back in 2016. So we'd had this theme of trying to do research in what we called in the wild at the time. So this was on Gear VR. The link goes to a modern version that runs on Oculus Quest, if you're interested. So that experiment is sort of still running. We're not logging any more data. You can still run it. So we had tried to do that, and of course then we had to do all of it like that. and as Wolfgang said, I had a big project that was building a new type of display, which basically got shuttered for 2 years, partly because we couldn't get in the lab, and then we were trying to buy some very specific pieces of hardware, which were on a very, very long lead time now, because they're in short supply and the manufacturers had problems and so on. So not shuttered, we did something else. We obviously didn't build the display. We went and did a bit of work on metameric rendering for virtual reality, which is more targeted in the graphics community. And obviously some PhD students sort of were very, very upset because they literally had, one of my students literally had an experiment ready to run, and it involved a biosensor, and yeah, trying to get one of those into people's homes is very hard. So we've run lots of studies online now, and to anticipate other questions, the reason we did it was because we had to, but it was a trajectory anyway, and then there's some lessons learned, and actually from that sort of things you've got to get right. So I'll leave. Well, I'll share these slides, and you can get the archive link. There was a workshop on how to run studies on VR under COVID at CHI last year, which we presented at, as did some others on the call. But the big thing is, it really did kick us. So I've been going on about social VR for years, and I'd written a book about it. I hadn't really done anything about it. Because I've been sworn off writing large software stacks. So this, COVID really did kick us into doing this properly. And we've just finished a tutorial this afternoon. There's more papers and more papers coming on this. We're trying to make it a useful tool. And so that's the big thing that we've changed. We were sort of displays and interfaces and very interested in that, but we've taken a big swing back into sort of the social side and trying to address some of the things that Amy mentioned about, how do people live with these things over time? How do we evaluate them? But to start off with, you've got to build a whole bunch of them. So hence this tool. And we have whole bunches of students building them for us. That's the URL for the tool, by the way, ubic.online. Right, thanks.
Thanks a lot, Anthony. I think we can move to the next question. What is your research plan for the upcoming years, Amy?
Okay, excuse me. So research plans for upcoming year, oops, wrong button. So part of my research plans kind of derive from a number of things. One of them being just trying to get back to those connections that Wolfgang was talking about. How do we increase those, both in terms of what can we do beyond what Zoom provides for us, and also what can we do in relation to combining what's happening in the physical world and what's happening in the virtual world in this hybrid experience. And so one of those, and then so the other side of this is just being that much similar to Wolfgang, I was in the middle of my sabbatical as well in 2019, and it kind of got cut short. And the one thing that happened was the connections and relationships that I established up until that point persisted, and so we were able to connect over these technologies. But I was having a hard time making new connections after that point. The technologies don't really lend themselves to offering or making those serendipitous connections where you might run into somebody and say, oh, it's good to meet you, and kind of, what are you working on? That sort of serendipitous social interaction. And so this past year, I've been very fortunate to kind of have a second go at my sabbatical at CU Boulder Atlas Institute. And so some of our research is just continuing this intersection of kind of what they are very interested in with creative technologies and music and making. And so one of the projects, I'm going to give a shameless plug to my student who's presenting a poster, where we're looking at how we can facilitate those connections in regards to music and jamming, and something that Zoom doesn't offer a very good platform for. So I'll just kind of do that video.
Whether it's trouble with latency, difficulty managing volume, or trying to communicate through a computer screen, people playing music all over the world are struggling to connect. And that's why we made the AR Drum Circle Android app. To use the AR Drum Circle app, first place your friends around the room and watch them appear as avatars. Your friends can play their drums, while the app sends a compressed message to your phone to move the avatar every time they hit the drum. The app also enables you to hear what your friends are playing in that same message, speeding up real-time communication. Now you can play the drums with your friends like they were in your home.
So one of the things that we're continuing to look at is, how we can facilitate communication, kind of going back to what I was talking about with the hybrid. If you're jamming using your headset, your head-mounted display, or maybe you're jamming with just your mobile phone, or maybe you're jamming with your augmented reality device, how do you connect together and offer a sense of co-presence in ways that, you offer visual co-presence, but how do you offer additional cues that allow you to understand where individuals are located, how perhaps your periphery is affecting your sense of where individuals are in that session, and how that affects stereo sound and things like that. So this is one of the projects we're working on in the near future. And then the next project that I'll highlight is something in which kind of going back to this idea that we're all kind of forced to go home out of the lab. Labs were closed, as Wolfgang was talking about. What can we use that's readily available for students, it's readily available for researchers to work on? And so that's kind of came about our project on interactive food. So how do we make food something that we can, you can find that in people's homes. And so this is just one example of everyday materials for food, everyday materials for interaction. And other examples are paper products, cardboard, things like that. So the group at the Atlas Institute in the Acme Lab are focusing a lot on using these everyday products for interaction and providing those capabilities. And then the last thing is that I want to mention is just that I think before the pandemic, and I don't know if it's just because of the timing and my sabbatical and things like that, I think I was very much thinking in terms of novel interface devices and interaction techniques based on those core interaction techniques of selection, manipulation, navigation, system control. And if I were to conduct a study on evaluation of those techniques, I would look at efficiency, speed, performance, things like that. And I think that's still important. But I think if you were to evaluate a creative interface or creative spatial interface, much like what I was describing with the AR drum circle, these aspects of efficiency, speed, performance may not apply to what the user wants to get out of the experience and what's important to the user in that moment. And so I think one of the challenges that I think we can look at in the future is how do we evaluate tasks in the VR environment, tasks in 3D user interfaces that go beyond some of these more traditional tasks that you would conduct related to exploration and selection and manipulation, and kind of looking at, you know, is it something that is more domain specific? For example, if somebody was painting in the VR environment, you would look explicitly at that task and see what's important to that individual. I'm not saying that's the answer, but I think it's something that as a community that would be important to look at. And as a result, I think creative spatial interfaces could be investigated with partnerships with individuals like designers, artists, creators, crafters, makers. And I'm sure a number of the researchers in this community partner with them already and other domain experts. But I think this is something that in the near future would be really important to look at. So I'll stop there.
Thanks, Amy. Wolfgang, what is your research plan for the upcoming years? You're muted. You're muted.
Thank you. Sorry about that. I was not planning to really talk with slides, but I'll roll over now and actually talk with slides. So I pulled out a couple of slides that talk a little bit about what my goal, my lab, my group is doing. And we're going strongly in the direction of professional level VR and AR. I mean, on the one hand, everybody agrees that VR AR works, right? But if you have ever played with a Varjo helmet, that's actually very, very good HMD. It still has wires. We could get rid of those. That would be nice, but that's basically an engineering challenge, right? And so I think it is time for VR and AR to go beyond games and entertainment and to target that, right? And also not target just the social domain, because there's lots of companies who are playing in that domain right now. So I'm not going to talk much about that. And this chimes. It sounds a little different than what Amy was saying, but there's actually a lot of commonalities when we talk about solving harder real-world problems, right? If you talk about an engineer sitting in and designing something for 8 hours using VR or AR hardware, you do run into ergonomic problems. You do run into lots of problems that have nothing to do with pure efficiency measures and so on, right? And you run into problems related to spatial skills. If they, sometimes people have more spatial skills and sometimes less, and can you support them? And all of these issues come up. And then partially the work that I did, Ufuk and me did was also to go more into training, see if we can actually look at the skill transfer. So I put up a list of challenges that we're tackling, and I'll very briefly talk about each one of them. One of the things that you notice when you interact in current VR AR interfaces is that precision, yeah, kind of nice, but okay. But if you want to put an object right between two other objects, that's still hard. And you can fudge it, yes, sure, but we actually don't have very good solutions for that. And that's necessary to tackle professional challenges where precision does matter. So that's one direction we target. Ergonomic interfaces, I'll pick text entry here as the classic example, right? Because the Google Drum keyboard is a great interface for entering text, and yes, you can achieve 50 words per minute, but you're not going to enter much text with that in reality, right? So, for example, the hockey keyboard that we published in 2019 is a very mundane solution for the problem where we basically took a tray, a hawker's tray, and put it in front of a person. And so you can basically stand or sit and type with a normal real keyboard in a lap. And that actually works quite well. As a field, I also think we have to deal with the fact that sometimes our technologies fail, right? Tracking failures, sometimes, you know, you go to the edge of the tracking space and you get a glitch, or somebody blocks a sensor and you get a glitch, and that can sometimes be harmless and sometimes can, in fact, your experience profoundly, right? Especially if you're, say, not just navigating, but if you're dragging and dropping an object and suddenly the tracking glitches and the object drops somewhere completely different. That's horrible from a user interface experience domain. Right? I think we also have a lot of work cut out in the depth dimension. What I mean here is that we have done some work, and this was initially published at CHI 2019 by Mayra Barrera, and where we looked at, and also in a VR paper in 2019, where we looked at how interaction with objects at different distances from the viewer, if that actually has an effect. And yes, this motion, straight forward and backward, is actually worse in VR than left-right. And so we actually looked at the reason, at the potential reasons for that. And what I'm very proud to report that together with led by Ufuk, and but also in collaboration with Mayra Barrera, we managed to show recently that there is a fundamental difference between single focal displays and multifocal displays for 3D interaction. So we built a multifocal display. That paper will appear later this year at CHI 2022. It's already on my webpage and some of my collaborators' web pages. But what it means is that 3D interaction is fundamentally slowed down when you interact at different distances from the viewer, right? If you basically left, right, everything that you do in the 2D plan that's orthogonal to you, that works fairly well. Right? But as soon as you get into the third dimension, the depth dimension, then you suffer from slowdowns and less precision and all kinds of issues. Similar to what Amy said, spatial skills, drawing in 3D, that's also something that we're looking at, because it turns out that some users very much suffer in VR, right? I mean, Mayra ran an experiment, is the best way to explain it, where she asked people to draw a straight line in a vertical line, and people curved the line because they just, you know, drew a line that basically was pivoting around their shoulder, right? Which, when you take a step to the side, you immediately see that's not a straight line by any means. Finally, there's two topics that are kind of blend together in some instances. Very dense virtual content can cause lots of problems. And so that's an interesting domain to tackle, but also large multi-scale environments. And so I'm thinking like from a house to a planet and back, or maybe to the solar system and back. So all of these still has lots of challenges, especially if you want to interact with them. And I think I'll stop here.
Thank you very much. And Anthony, what is your research plan for the upcoming years?
Get famous and retire rich.
Okay.
No, sorry. Sorry. No, so I have a lot of similar, lot of interests similar to Amy and Wolfgang. So what I want to try to do is say just two things that I think are really motivating in our lab. We're working on lots of different things. So sort of body ownership illusions, narrative engagement in VR, mixed reality systems, collaborative systems, so on. And one of the big directions I already mentioned is this sort of social VR this direction. So that's at least a third of our work now is on sort of social VR and improving its uses of technology. one of the things that we are developing a lot of projects on is just the general issue of accessibility to these tools. So this is a sort of, I'm sure Wolfgang is, some of his work is motivated by this, but this is the motivation on itself is they're not very accessible. How do we make it accessible as a technology, but also as a media form? You show most people metaverse and they run a mile because they've seen, they've seen pictures of people that sort of have a sort of version of locked into these systems, or it's going to be like going to Oxford Street in London on a Saturday, which you don't want to do, by the way. It's crowded with people. Not all of them wearing masks. So just making it more accessible, making it more content friendly, sort of getting more content in there, dealing with how you onboard people and so on. So all the things, this is all sort of the sort of hard to do in the lab sort of HCI of VR. I got very interested in that, partly through the consumer VR, partly through some work we are doing on direct accessibility for people with motor impairment. Coming late to the realization that the one thing that they wanted to do was play VR games, not the first thing they said when we did focus groups with them is they want to play Half-Life Alyx. They don't want to be trained. I want to do exercises. They just want to play VR games, and so there's a growing accessibility community there. So not just that. This is the whole sort of how it's perceived and how you get access to it. And the final area is keep me busy for a very long time, which is haptics. So we haven't got a tradition of doing haptics, but one of the reasons I went to Microsoft was because they've got a good reputation in haptics and mostly handheld devices, and I went along and said, well, I don't think that handheld. What about hands-free and haptics? And so I did a project. The project I spent most of my time there was actually a shape-changing robot, which is eventually now being published in Nature Communications. So we built a device that actually changes shape. It's effectively a physical NURB, and it changes shape. You put your hands on it, so it's a whole hand display. And we are just looking at the sort of how do we want to do this in the future, and how on earth do we get there? Because you've got output devices with millions of degrees of freedom, right? Not 6 or 3, 7. We've got one with 12. It's whole shape, or it's illusions and smaller dimensions. So that's really motivating, but it's a very long-term thing, that one. And we don't have much work on it yet. We have the thing I built at Microsoft, which I've now built one in my lab, and I've made it better and added a new feature, and I'll be trying the US deadline for it. Yeah, so 3 things: social, accessibility, and haptics.
Thanks, Anthony. We actually out of time. That we actually have 2 more questions that I prepared for the panelists, but we are just close to closing time. We already passed that. So I just want to ask the audience that if there are any questions, is there anything that you want to ask?
I apologize. We all talked too long. I mean, especially me. So I apologize on everybody's behalf.
No worries. That's why we are here. That's so we can just get some ideas, some perspective. So that was great. Any questions? Just let me check also from the Discord channel. No, there are no questions in Discord. Are there any questions in Zoom?
I guess I have one question. So I think now that VR devices are becoming more popular, and talking from Anthony talk, do you see a change in the type of participants we will get in user studies and so on? And how would that affect our research?
Actually, Maya asked one of the next question. So yeah, please go
on. So I can quickly answer that. You get a wide variety of participants, but you do get VR users. So they are biased, and it's a different bias than engineering students. But yes, and we one thing we're doing is working with more sort of outreach organizations that actually take things out to schools or exhibitions and libraries and so on. So yeah, so actively reaching larger populations for experiments is an ongoing challenge. We thought we'd put it out and there are millions of users, but they're fairly homogenous at the moment. They're not homogenous, but they're not trend young and lots of experience with gadgets. Yeah.
One of the things, thank you, Anthony, that's a beautifully said. I want to add that also the spatial skills vary substantially across people, right? I mean, if you get the people who are VR enthusiasts, spatial skills are typically fairly high in that crowd, right? And if you get people who are not from that crowd, you observe very different outcomes sometimes. Just want to add to that.
Amy, are there anything that you want to add?
I think they answered that very well. Thank you.
Okay, perfect. So thank you very
Yeah,
much.
thanks.
Yep, thanks. I will just share my screen again, and I am going to finish NIDIT this year. So closing comments. Thank you very much, everybody. Thanks for coming. Thanks for joining. Like that was a really nice NIDIT for this year. I want to thank all the organizers of the NIDIT this year, Francisco Ortega, Rob Tedder, Wolfgang, Adalberto Simon, and the Benjamin Wares, that they were really, it was a really nice group, and I really like working together with these really good researchers. We hope to run NIDIT for the next year, for 2023. Hopefully it's going to be the 5th year of the NIDIT. But in the meantime, if it's possible, maybe we can just make a surprise, and we can just have the NIDIT in other platforms. Who knows? If you want to organize, if you want to help organizing the whole NIDIT, please contact us. That you can contact with the you can contact me, Francisco, and Rob. And for the next year, again, please watch the the call for papers, and again submit your paper. Hopefully, next year the NIDIT will be in person, so that we will ask our authors, the paper submissions, to bring their devices, their input, the VR technology, their new device, anything like they develop, so that you will be able to try them in person. So that you can just ask direct questions and experience that the new thing happen. So that would be a really, really good challenge, and that's going to be really good improvement for the IEEE VR. There is one, let me check. Yeah, so thank you, everyone. I hope you will enjoy the rest of the IEEE VR, and please get in touch with us if you need anything, if you have any questions, or if you want to help to run the NIDIT next year. So have a nice evening, day, or night, or afternoon. Take care.
Thank you. Thank you, everyone.
Thank you. It was great.
Thank you.